Great. I think we'll go ahead and get started. Welcome to all of you joining us here in the room or those joining online. This is your first time joining. My name is Scott Williams. I'm the Research and Education Coordinator here at the Wisconsin Energy Institute. And the Sustainable Energy Seminar is something we do every other week in the fall and the spring semester with the goal of highlighting cutting edge energy research here on campus and to showcase how different disciplines understand energy challenges and develop solutions. So throughout the series, you'll hear from folks in science and engineering, as well as the social sciences and humanities, to understand and learn about the ways in which they view sustainable energy challenges and solutions. The seminar is open to the public, but it's also a class for the Certificate in Engineering for Energy Sustainability, as well as the Master's in Sustainable Systems Engineering. You can see this is presented in a hybrid format, so we have folks joining online, in person. For those who are joining online, feel free to introduce yourself in the chat. If you have a question for our presenter, please use the Q&A box and I'll be monitoring that and asking those when appropriate. And we'll try to alternate during Q&A time, alternate between online and in-person questions. We do also have live captioning available. You can just hit the live transcript button or the show caption button within Zoom if you need that feature. With that, I'll introduce our guest speaker today, Giri Venkataramanan. Is a professor in electrical and computer engineering, and he's also the director of the Wisconsin Electric Machines and Power Electronics Consortium. His research program broadly covers major aspects of power conversion systems in different application areas of electric power generation, distribution, transmission, and utilization systems. So different power conversion devices, power electronics, industrial drives, microgrids, lots of different applications. He also has a very specific focus on energy sustainability and technology access. And so when I asked him to give a presentation, he came back with this title. I was a little befuddled on what the topic was going to be, but once he sent more details, I'm anxious to hear more about his view on Jevons Paradox and how that relates to sustainability. So welcome.
Okay, so thank you so much for inviting me, Scott, and also joining me this afternoon. And he not only invited me to give me a talk, and he said you can talk about anything you want. And so I wouldn't pass an opportunity like that. And so getting on the pillbox, talk about Jevons Paradox, which is one of my favorite topics and related to energy. I don't get to talk about it ever, except in sort of dinner table conversations. And so I'm happy to talk about this for this group as well as in public, because there's a lot to learn about energy and sustainability from this perspective. And I don't know if it's a paradox. If I had a choice, I would call it Jevons Law. Okay, move this. And a little closer. How does that work? Maybe I can hold that in my hand. Yeah. Okay. Does this work better?
It should be on, yeah.
Okay. So I'll use this as you heard about it. So this is related to decarbonization and Jevons Paradox. And I want to take you on a little tour backwards in time, not all the way to the Big Bang, but maybe a few hundred years ago. This is 250 years ago. And what you see on this picture is a portrait of Matt Bolton. He lived from 1728 to 1829. And so one of the quotes that's attributed to him is, "I sell here, sir, what all the world desires to have, and that is power." And that was him speaking to James Boswell about his engineering work. And James Boswell's wrote a book, Life of Samuel Johnson, which in the sort of the English literature community is a well-known classic. I would say it was perhaps one of the first biographies. And Samuel Johnson was the one who put together the very first dictionary in the English language. And so this is something I liked, this quote, and I've been using it for probably 30 years or so. And I tell myself I sell power electronics and power conversion. My lineage goes back to people who are cutting firewood or picking coal from the mines in Newcastle. So the energy business drives everything we do. And in about 50 years after that previous slide I talked about, this is a picture of a sculpture or an installation in Birmingham. It has Matthew Boulton and James Watt and William Murdoch. And many of you will know James Watt. And Watt is recognized and acknowledged for his unit for power, say kilowatt or megawatt, watt hour, that is James Watt. And James Watt and Matt Boulton together did a lot of improvisations to the steam engine. And their main goal was to reduce the amount of coal used, make steam engines more efficient. And they became very successful. They were very successful. James Watt and Company was what eventually it became after Boulton passed away. It transformed the British industrial landscape. That is before early 1800s. And the world we know of today that consists of what we think about industrial revolution, steam engines and railroads, all that was a big growth that happened in that space. And so that's all history. And 50 years later, after this revolution took place, this is 1868, and William Stanley Jevons is a professor and lecturer on political economy at Owens College in Manchester. He gave a talk at the Royal Institution of Great Britain on a weekly evening meeting on Friday, the 13th of March. And it's probably similar to this meeting today. On a Friday evening, they probably had a few mugs to share and to talk about what would happen, the probable exhaustion of our coal mines in England. And Jevons had already published a book on coal, the coal question, a couple of years before 1868. And he was a professor in political economy. But he got very interested in coal at that time because it was right after the corn stuff that was going on in England. And many of you may recall the name Malthus, the Malthusian thing about population. Malthus was worried there will be no food left. People will all die. And that led to passage of corn laws and other things. Anyway, people didn't run out of food. But then Stanley was was asked by somebody in the government to look into this. What would happen if there is no more coal left? And so Jevons did a lot of very, very meticulous study of what James Watt and Boulton did on improving coal and how it had transformed the British landscape. And he posited this, he wrote this book, and in there he talks about this, what we call paradox. He calls it a confusion. So we'll talk more about it as we go. And so in this in his presentation to the Royal Society, Royal Institution, I'm giving a gist of what he talks about, and the text of the presentation is available. Any of you look in the internet, UW-Madison Libraries carries an online copy. You can look at his talk. He talks about 8 or 9 different points, and I'm bulletizing here. So at that time, in 1866, 2 years before he gave this talk, England was using 100 megatons of coal in that year, 100 million tons of coal. And today, we're using about 8 gigatons worldwide, only coal. Just to put ourselves in perspective, England was using that much already at that time. And he also calculated this was equivalent to 2.6 billion people working 8 hours a day for 300 days a year, only in England. The amount of coal that was used. So we think about the colonialization and all the growth that took place in India, in England, look at London and Edinburgh, all that. This was what fueled all of that growth that happened before 1866, around that time. Today, this 2.6 billion people is all the people between 20 to 40 years old in the world, approximately. Let's say all of us are working towards growing England worldwide. And that is the equivalent of coal that was being used. So Jevons talks about it. He wrote did very meticulous calculations on that. And this was used for household, industrial, electricity, light, motive power, everything. And then calculated that coal will last, the coal that was in the ground in England will last 835 years at that rate. So nothing to worry about. If it was going to be at that rate constant. But the red item was what Jevons Paradox is that coal use is growing with the economy in spite of what all James Watt did, make the engines more efficient and everything, the efficiency continuing, coal use is growing, and he said it will last about 100 years after that, 1866. And what he said was the growth is geometric, and he also does a comparison worldwide. He looks, and this is in the small talk. His book is wider. I had given a link to that for you all to read, and most of you probably skimmed through it, maybe first and last chapter. But this is essentially a short, let's say, what is that, Cliff's Notes, cheating notes for what is in Jevons' book. Now, was he right? Okay. He was almost on the dot. So this is a picture, UK Department of Energy and Climate Change, coal production and imports in the United Kingdom, 2020, they ran out of coal in England. And they would have probably ended it here if they had not imported, or the stuff that happened during First World War, other things had not happened. He was on the dot. So Jevons Paradox was proved in England by the ideas that he put forth in place. And okay, so that is one data point in here. And so this is looking at the energy intensity per GDP in the US. And this is from a book recently written, Empirical Evidence for Jevons Paradox. So between 1960 to early 2000, we used less energy per GDP, about a half. From 12,000, we were able to get the same economic output with less amount of energy, about a half. if this was true, if GDP was steady, you would expect we would be using half as much energy as 1960. In 40 years, our energy use would have gone down by a factor of 2 because we started economizing, particularly after 1970, the first oil crisis. After that, we have a steady line going down. And beyond 22, more data is not. This is from this book where I pulled this data out. So we would expect energy use to be going down. Did that happen? Energy use went up, almost double. From 1960 to 2004, almost doubled. And again, this is again from this book, Empirical Evidence for Jevons Paradox. If you get a chance, you should read it. An excellent book. It's available online from our library as well. So energy use went up. This is another piece of evidence for Jevons Paradox at work. Okay, here's my little cartoon of what Jevons Paradox is. Go to Babcock Ice Cream. They say, hey, we found a new ice cream that only has half the calories. I'll take a triple scoop. That's what we're doing. You know, the society together, we're using more energy because we think we've become more efficient. That's Jevons Paradox in little quick terms. So let's look at other disciplines where the impact of this in places we're looking at. First was coal and steam. Let's look at what's called Moore's law with this number of transistors in integrated circuits. We're probably carrying 1 million integrated circuits in our pocket with our mobile phones. And so this is looking at the transistor count as a function of time, and it keeps on increasing as time goes on, and the vertical axis is logarithmic. So we're putting 1,000 transistors versus 20 million. Is it million? No, it's 20 billion transistors per chip. And this is what is fueling our information computing revolution. It's called Moore's law, coming from Thomas More, founder of Intel, recently passed away. And Moore's law is well understood. Any computer engineering student will tell you about Moore's law, what it means. It means when he posited it, it says every 18 months, the number of transistors in a chip will double. And so this drives our economy today, worldwide. There's a parallel Kumi's law. And Kumi works at Lawrence Berkeley Lab, sort of an energy geek like many of us. And he looks at computation per kilowatt hour. How much computation can you do with 1 kilowatt hour of electricity? Over a period from the vacuum tube computers all the way to now. And before vacuum tube computers, we had mechanical computers that had motors and gears. It was put together by Turing during the World War. And so the amount of computation we're doing per unit energy is going up. Impressive increase. With the same amount of energy, we can do so much computation. And it's also logarithmic. This is 1,000. And we're looking at, I don't know, I can't say how many zeros there are, 16 zeros. And this is Kumi's law. And this is an IEEE Spectrum article. Moore's law might be slowing down, but not energy efficiency. It continues to get better and better and better. So what do you think about the energy use for computing? Should be going down, right? Okay. total energy used for computing, billions of kilowatt hour. So Kumi's loss, energy per logic operation is going down. It's inverse of the previous graph. It's Kumi's law, Kumi upside down. But the amount of energy we're using is going up. This is Jevons Paradox at work. Because we've made the energy cost per computation so low, we want to use that for multiplying 2 and 2 together to get 4. It's so cheap to use that rather than using my brain. For everything, we use computation. We don't do anything else without computers. Because of the price per computation is going down. And this, by the way, is from Mr. Mark Mills. You can look him up. He's a prolific writer, has a website, and he's an energy guru. And he put together a report about 10 years ago. And surprisingly, this report was sponsored by National Mining Association and American Coalition for Clean Coal Electricity. So they're very, very interested in knowing what's going on because it's a market for all of these fuels. And okay, so that is going on in the computation field. This is total digital traffic. Amount of digital traffic that's going on. Petabytes per month is 2015. Today, after COVID, is probably, I don't know what, peta squared. That's probably how much global traffic we have. And so that is communications, lighting. Lighting efficiency, fire, which is candles, incandescent lamps, fluorescent lamps. Now we have LEDs coming up. The amount of lumen hours you can get per dollar is going down and down and down and down and down. The latest thing is incandescent lamps have been made illegal to sell and manufacture in the US. And LEDs are replacing them. The amount of illumination consumed by human beings keeps going up. The amount of lumen hours that we're putting in keeps going up. If I were to use the same amount of lumens than the candle was used, I will have one LED lamp in this room. Okay? These are LED, what do they call it? Luminaires. They're using very little energy, 3-4 watts. We replaced our compact fluorescent lights in our home with LED lamps recently, but more lighting is used now. I know from personal experience. And all the Christmas lights are now LED lamps. It's only 2 watts, why not? We're buying a lot more. So lighting companies are licking chops because we're going to buy more lamps, more lights for everything. It's only LEDs. Instead of 1 flashlight, take 5 flashlights, 1 in each pocket. That's how we're working on this. Airline traffic. This is interesting. Number of barrels of oil per 1,000 passenger miles from 2 in 2015, this 20 years, better than airlines are more fuel efficient. They've done that through various things for how the aircrafts operate. Global traffic, trillion passenger miles going up. And so we're looking at passenger miles and energy use per passenger miles in here. And ongoing work, as you know, some of you may be aware of aircraft electrification. Aircraft are going to be electrified just like cars are being electrified. Hybrid airplanes are going to be coming up very soon, maybe 5 years, 10 years, 15 years. Ongoing research by various aircraft companies will make this even further down. And the government is also supporting sustainable aviation fuel, SAF development, to help improve this energy efficiency for air travel, but we'll only be flying more. And this is related to 5G. This is the Internet of Things, various things that are going up. We have total amount of energy that's being used. The places where you have data centers are big hunks of energy use where we route the signals in and out. But we're carrying many of these in our pockets. Internet of Things. Now all our phones are connected to internet. All the LED fixtures will be connected to internet. I was in an installation in the University of San Diego earlier this month, or early September or late August. They have a few of the luminaires in one building that are connected to the internet. They're looking at improvements in energy efficiency to offset all these things that we're working on. So this will keep growing, okay? So you want to save energy, spend a little bit more energy so that we can use more energy, right? So are we doomed? And at best, decarbonization can be a temporary fix. That's my perspective. And this is in Jevons' words from his book. And he talks about, he wrote this report at the request of the Royal Institution or people that work in the UK government. Just like these days, they'll ask a university professor, can you look at it and tell us what's going on? So this is what he wrote. Our empire and race comprises 1/5 of the world's population at that time, 1/5 of the world's population, or British. The guardianship of states, plantations of new states. US was not an independent country at that time. It was an English colony. US was still a colony. And by penetrating commerce, an example of our just laws and a firm constitution, UK doesn't have a written constitution. So the firm constitution, above all by the dissemination of our arts, we stimulate the progress of mankind in a degree not to be measured. However, as we go through this, but what he says with this cold question is that the maintenance of such a position is physically impossible, he concludes. And this is 150 years ago. We have to take a momentous choice between a brief but true greatness that was enjoyed by the English British Kingdom that day, and no longer continued mediocrity. He's worried that the country will become mediocre. And so did this come to be true? No. Okay, so we'll continue our discussion here. Are we doomed? So I'm going to switch over, talk about something different. Yeah, sure. Yeah.
So the first question from Raj is, would you link increased productivity with increased energy consumption and people having more time for hobbies, recreation, and companies are run more efficiently?
Absolutely, yes. But all put together will be consuming more energy. And I want to make sure I'm mindful of time. And so Jevons is considered among the founders of neoclassical economics. What we say supply demand, he was the first person that put math around it. And so it's a very, very important observation that he made. We have to take him seriously. But we have an entire discipline called ecology that didn't exist. Ecology and economics come from the same word for eco. And so we have a move, we can move forward and get beyond Jevons Paradox. And I'll spend the rest of my presentation on that. So in economy, growth is sustained. That's a fundamental law of economics. Marketplace will provide solutions no matter what. Run out of resources, marketplace will find solutions. Run out of energy, marketplace will find energy. Economy favors large scale, and waste is externalized. We had to find landfills or emissions and whatnot. And nature belongs to us, we will just extract. The ecological perspective, on the other hand, the transformation is what sustained. We're constantly transforming ourselves. The earth transforms itself. The system transforms itself. And the solutions arise through diversity. There's so many diverse solutions. And resources feed each other. Resources are not consumed. More waste from one place, feedstock to the other place. Energy is consumed. First law of thermodynamics holds for any ecologist. And diversity in scales, not big is the better. There's big and small and medium, all sizes, all work together. And we belong in nature. These are the ideas from ecologists. So let's look at one of the works from an ecologist, Nature Geoscience publication, 10 years old, probably updated, but I was able to find a picture that talks about Earth's energy imbalance. And the imbalance is approximately 0.6 watts per square meter. That's the amount of imbalance that was measured at that time. Since then, there's more data and other things coming up. But the surface imbalance is 0.6 plus or minus 17. Look at the uncertainty there. This has to do with what we do on the surface, burning and various other things that happen in there. But it's a very interesting paper. I want to invite you to go and read if you get a chance. But I don't want to dwell upon that, basically not go away from the story I'm trying to tell. So if you look at the energy cycle on Earth, there's a lot of stuff that's ongoing. Biological activity, there's volcanoes spewing stuff, wars going on, animals and trees, what happens, fish inside oceans, stuff that's buried in there. You'll see this fossil fuels are being pulled out by us. These were sequestered there for millions of years by Earth. And this naturally takes place as a shock to the system. Nature adjusts itself. We get into trouble when Hawaii erupts. So if you look at the natural systems, it's always a circular economy. And that how nature and biology works together. Nature has been doing this millions of years. Changes, transformation continue to take place. There are raw materials come in here. This design new beings, new biological creatures. They produce, manufacture carbohydrates and various other things. It gets distributed, people carry them. They themselves move, migrate, and it's used by other animals, other plants, all scales, unicellular all the way to the most complex. All of this is going on in a circular economy. What's mainly coming from outside is sunlight. And the residual waste actually doesn't exist. It gets cycled into the system. In fact, it's what is surplus. This is what we have buried inside the fossil fuels. They were residues that we're using today. This is how the circular economy works. And if you look at that circular economy, using these elements that are very abundant. There's also a vertical scale as a logarithmic scale. Oxygen, silicon, sodium, calcium, potassium. C is carbon, important element. The nature chose carbon cycle. It did not do a silicon cycle. It did not do a uranium cycle. So someplace else, out here. It used carbon to do its work. And nature's evolutionary process would have tried other things, because nature tries so many things every day. And it's been doing that for millions, billions of years. 40 billion years is when since life was formed, according to biologists. So if we're looking at lithium cycle today, lithium batteries for various things. If lithium batteries would have been practical for a circular economy, nature would have figured it out. Because it has been working on this for 40 billion years, not 200 years. So I'm big on carbon cycle, water, hydrogen, oxygen, nitrogen, everything that's in this area. And so decarbonization is not what we want. We want to recarbonize. We want to retain the carbon, but we have to close the loop on it, not let it open. And this is an advertisement of one of the presentations from somebody who was in the audience today. And this is October 5th. What, a week ago? Less than a week ago. Advancing Sustainable Energy Solutions, a Circular Bioeconomy in Wisconsin. And we're right on the dot. And this will all help us overcome Jevons Paradox, because we're going to close the loop on this and stick to carbon, because bioeconomy, there is no bio without carbon. Bio is carbon. Okay, plenty of choices ahead of us. Survival of the fittest. And then here's a picture I pulled out. Some of you may recognize, this is a Amish buggy riding on a asphalt road in rural somewhere. So this is a lifestyle that's viable too. And you may want to know the population of Amish is doubling every 20 years. In a few hundred years, Amish population will overtake the non-Amish population, because the rest of the population is not growing. And their lifestyle is very different from our lifestyle that's standing around this room here. As that grows, is that going to happen? Well, we don't know. So a lot of choices ahead of us, and times they're changing. So also from the same book, the big problem with we use the word tragedy of change. Change is not easy. The choices related to sustainability are choices that require reflexivity and the willingness to change yourself in order to be able to co-evolve with other humans and the environment. That's what's going to take us to move into that closed loop bioeconomy. And that loop can grow. There is no limit on it, because it's constrained by the ecological laws on conservation and diversity. But we have to figure out how to do that. Just now we're starting to talk about it. There is so much work to do. So change is hard, but minds can change. This book is our campus choice for Go Big Read this year. It's a very interesting book. It's available free of cost. If you go to the website, ask for a copy, they'll give you a copy. And David McCraney is going to be on campus first week of November to talk about his work on this. So change is coming, we have to change if we want to overcome Jevons Paradox. So Jevons himself, the very last closing words in his talk is this. He says, if we do not use the abundant wealth to afford such duties, we will undoubtedly misuse it. And what should we do it? Standard of education, comfort, and morality of the people. We have to work on having discourses talking about all of this. Morality is typically a bad word, but we have to talk about it. Comfort, our own comfort, and education. So he didn't give a message of doom towards mediocrity. He gave a message of a positive message that we have to continue to work towards finding the truth. And my opinion today is ecology is where the truth is. Circular bioeconomy, carbon cycle is where the truth is if we need to overcome the warnings that Jevons gave us. Thank you.
I'm just going to turn on the.
Okay.
Any questions from here in the room? Got a few questions online.
Yeah.
So I think going back to maybe some of those graphs we showed, the increased efficiency and increased use. Were some of the Anurag asked, some of these statistics controlled for population growth and access to technology, more people using energy that weren't until costs were lowered and access was improved?
Yes, absolutely. So if you take this one, the access is improved. Particularly, this is one that I like a lot. Maybe digital traffic, or this one, the availability of inexpensive communication devices. This is a place where equity has played an enormous role. 50, even 30 years ago, we said everybody in the world, almost everybody in the world will be able to communicate at will to anybody else. We laughed. And today, the penetration of mobile phone technology around the world is just phenomenal. Nobody says Africans are too poor to have a phone with them. The equity of that technology is reached across everywhere. Is it the same everywhere? Is there equity on every technology? Not so. And it has to do with how governments have worked, corporations have worked, how the market has worked to provide that access. So it has improved access. So it is not having new technologies improving efficiency is not something we should not do. We should do it, and more. We have to, and if we don't close the loop in this carbon cycle, we're going to leave it.
Next online question, Uni asks, it seems there's an implicit assumption of causation in this paradox. The increased energy efficiency leads to increased energy use. Why isn't it the other way around? For example, because so many people travel on airlines, airline companies have found ways to increase the efficiency of planes to improve their bottom line.
Yeah, I think it's a very important point. Like Moore's law in terms of transistors per chip is considered a self-fulfilling prophecy. So in many of the companies, improvement of efficiency of their system is built into their roadmap. So it's not one leads the other, it's chicken or egg. They're both doing it together. And the push and pull between the forces of where the researchers and creative people are working and the demand, they're both in concert together. So it's not one leading to the other, but they're both marching together to each other's band. They're beating the drum together. Yes.
come across any arguments or maybe quantitative analysis on the role of this paradox on negative emissions technologies? The more we're pulling out of the atmosphere, there's complacency on emissions reduction process.
Yeah, I'm not aware of any work. So let me repeat the question maybe. Is there any work done on the impact of Jevons Paradox on negative emissions technology? I would expect you mean the sequestration? Yeah. And so I'm not aware of, I did some little bit of research after I offered Scott to talk about this, and I couldn't find any. But my own personal perspective is that trees are doing it really well. And they're ready-made available today. We can invest in new technologies as well, but trees are already biological. They belong in the carbon cycle. They know how to destroy themselves. In the fall, they fall down, they burn. All of these things happen. So I'm sort of a deep nature person. So if it's already invented, why reinvent it? And maybe I want to take this opportunity to add a little bit of perspective on efficiency of energy conversion. Efficiency of energy conversion by plants and the animal kingdom is mere 2 to 6%. But they know how to close the loop. The best machines, electrical machines or generation systems we can build can reach 60 to 90, 98, 99%, but we don't know how to close the loop because plants have figured out how to close the loop. So I would say all of these structures would have to be wooden structures, sustainable, FSC, for Sustainability Council. And you may have come across stories about how Norway has built a really beautiful public library using only wood and nothing else. Another skyscraper in Hong Kong. Skyscraper, this is like 200, 300, 400 stories high, all with wood. But it has to be done so the loop is closed and not just cutting off trees. And so more work for us to do. Thank you for asking that question. Yeah.
More questions online. One person asks, is there any relation between increasing energy consumption and life expectancy with improved health and living conditions?
Yes, absolutely. I had an image on population growth versus energy use. And our population is supported primarily through increased use of energy. It involves various other things: availability of food, availability of healthcare, availability of facilities for structures that can manage large populations. Everything ultimately goes to having energy. And so there was one quote called Energy Propulsed Society. And all of the advances we consider happened over the last 250 years can be traced back to availability of energy and improved energy use.
Right, another online question. What would you say is the role of researchers and universities to advocate for more ecologically aligned systems as alternatives to capitalism?
I don't want to get into capitalism. That word is not something I want to rag against or for. But ecological alignment of our processes, I would say, I'm a faculty member of the College of Engineering. Many of you are taking the certificate for energy sustainability, which I'm pleased. I would say if all engineers learn about ecology, and this book that talks about empirical evidence of Jevons Paradox, these transformations are not overnight. This will take generations. And the thought process that Jevons started out in supply-demand equilibrium and mathematical formulation of economics is where we are today. It's considered common sense. We increase the supply or supply-demand equilibrium. I'm not an economist. I'll dig myself into a hole if I talk more. But the ecological principles have to drive our society, and universities have a very large role to play in educating the future generations and getting us all sensitized to this ecological way of looking at engineering, life cycle costs, landfill, waste, all of that we have to invent and innovate.
Kind of along the same lines, could you elaborate on actionable steps or technologies that you'd recommend for transitioning to a circular economy in the context of sustainable energy?
So the people and the folks in the field of agriculture are far ahead of us in life sciences. They've already figured out ideas of permaculture, developed models for organic food cultivation, various other things that looks at the soil cycle, nitrogen cycle, and various other things. They can grow food without a lot of fossil fuel inputs. And so that is one place we can easily start, all of us, because we consume food. We can think about transforming our food consumption, connecting with, linking us more with the circular economy so that that part, it's still a very small percentage of the food industry, but it can grow, and we can learn from the food economy on terms of buildings. That is starting to happen. Our professor, I forget his name, we had a class called sustainable residential construction from biological systems engineering. And so how do we have buildings that consume less materials, that consume less energy? In all of these, closing the cycle, one of the important part is the 4 R's: reduce, recycle, reuse, whatever those 4 R's are, which is reduce is a big part of it in terms of how we consume, what we consume, use more carbon-oriented, organic-oriented clothing stuff, cotton or wool versus polyesters, synthetic materials. And if everybody stops wearing polyester materials, cotton will grow and synthetics will go down. So a lot of things we can do, and each of you has to figure that out. And I'm not a guru on this to get on the pillbox and tell you how you ought to live your life. Yes.
I'm a graduate student in agroecology, actually. I wanted to ask, from a general perspective and from an agricultural perspective, what do you mean exactly by closing the carbon loop?
Yeah, what do we mean by closing the carbon loop? What do I mean by it? Right now, we take stuff from the ground, fossil fuel, burn it and put out. And that is the open loop. So look at the picture that I showed here. Looks like my screen doesn't want to respond. Something. Oh, all right. This loop, you'll see all of them sort of give and take and close in on each other. This particular loop right here is an open loop. And the volcanic eruptions and things like that are rare events. They do play a role, but they are the ones that came into here from activities millions of years ago. And that is still a closed loop. And we're opening it up, and how do we bring it back and stick it into the soil? And the driving force is this energy imbalance. And trees have figured out the energy imbalance. It's like the bank. You know, our cash flow is not going to be same year round, monthly, seasonal variations. And the excess carbon gets absorbed, turned into leaves and fallen down, and then gets sunk into soil and it gets cycled in. And some event comes in and then pushes everything down. I don't know, I'm not a geologist, but I can understand a little bit at the 4th grade level. And I know that this doesn't fit that process. And that is what I'm saying about closing the loop. Does that make sense? Yeah.
Do you have another question online? Would you see Jevons Paradox applying to decarbonization in the way that decarbonization is expensive now and technology seeks to drive down costs and make it more efficient, and then that could potentially drive greater decarbonization too, as a flip side to increase energy usage and carbon emissions?
That is my biggest fear. Will decarbonization lead to more carbon in the atmosphere?
I think the question is more, will it lead to less because we're getting better at decarbonizing with its solar technologies or other?
Yeah, that is moving away from the carbon economy. And that will affect this energy balance by capturing light and putting it to a new economy. That's a silicon economy. And when you look at the wind turbines, there's a lot of hidden costs on waste that comes from the towers and the blades. Mark Mills that I mentioned, he's written a lot about it. And so it's still not a closed loop yet. What are we doing with the silicon after these solar panels run out of their life? So we got to think about the silicon loop, various other lithium loop. All of these are important things for us to consider. If we're opening new loops in there, let's close it. And that is perhaps maybe in addition to the closed carbon economy, trying to how can we close the loop on every other resource we're consuming is perhaps a very challenging aspect for us. You have a couple
it sounds like it's actually necessary. Actually obvious. Look at it logically. You have to close all the loops because otherwise you can't exist forever. At some point, you're going to run out of something critical. You have to recover.
Right. Thank you for bringing it up. We have an audience comment. Closing the loop is a critical aspect. If we don't, we're going to run out of something at some point in time, or you end up with whatever you have transformed into something else. We cannot put the genie back into the bottle. Yeah. Thank you. So one more question here.
In your discipline, lecture, right? We're struggling with smaller loops, like your typing diagram is surrogates for the closed loops. And nuclear engineering is an important one and has a longer, more complex cycle and not understood cycle. And it may be one of many transient loops. And so the question now is there any hope, or we're thinking right now of battery technology which creates storage, will create one of these short loops? Or is it, yeah.
Yeah. So I think you're raising an important point. I think that's what I was trying to saying here. What we're doing is a temporary fix. We can look at batteries, lithium cycles, silicon cycles, they're all temporary fixes. And my thing comes from, it's not, why would I say it's not permanent? Nature would have done that. It's been doing this for much longer than any of us can visualize. And that is something I would say when I look at a tree, what am I learning from it? And so I wouldn't say rule it out, and I think those are all temporary fixes, but we sort of have to sensitize all of us that closing the loop is part of our DNA. And that'll take us a long time for us to go there. And even the literature is just starting to come on smaller loops, bigger loops, system-wide things. But I think it can happen.
We do have a couple more questions. Do you have a couple minutes to stay?
Yeah.
Okay. So one question is about, can decarbonization technology slow down carbon extraction from the atmosphere, like hydrogen boil off may slow down methane depletion from the atmosphere?
Yeah, that's again above my pay grade. You gotta look at Professor, what is her name? One who works on there. Tracy Holloway. She would know a little bit more.
Then someone asked, would you consider biofuels a fully closed loop?
Oh, biofuels can be a fully closed loop. What type of inputs went into the biocrop? Is it again fossil fuel? Is a question to be asked. And so it's not necessary that it has to be a closed loop, but it can be a closed loop.
Right. And then did you have a slide with your contact info? Someone wanted to.
Yeah, the very last slide.
Right.
Yeah, there's my email address. Feel free to email to me. If it's interesting, I will reply back. Otherwise, it'll stay. Eventually, I'll get to that.
All right. Thank you very much.
Thank you so much, Scott, for the.